Okay, let's get going. We have a whole bunch of stuff to cover today. I don't think we'll get through it all, unfortunately. As you know, we're still a bit behind based on the fact that the weather has not been cooperating. Somebody said in lab the other day, and it was absolutely correct, that it's hard to get into a routine now, because there is no routine. For instance, next Monday's class is canceled already, right? There is no, because it's a holiday. But what it's doing, it's actually not canceled. It's postponed until Thursday. So we will have 2 classes next week, barring any more acts of God. Hopefully things will be settled down by then. So today we are going to talk about these things called sets, and we're going to go through that really quickly because I'm never going to make you actually build a set. If you've already looked over this week's or the current homework assignment, you will have seen that there's a set in there, but I built it for you. We will have to know about what sets are, what the abstract data type of a set is. We'll go through that. And then we're going to talk about queues. Notice this line here. Anybody from a Commonwealth country, Great Britain, Canada, somewhere? Where are you from? Zimbabwe. You would call that a queue, wouldn't you? Right? Those of us in the United States might call that just a line, or something like that, right? But if you're from a Commonwealth country, that is what a queue is. So you say, oh, we stand in a queue, right? So you will hear that if you're from Great Britain or Australia or something, right? But that's what we're going to talk about. We're going to talk about this idea of first in, first out, instead of a stack, which was first in or last in, first out. Okay, so we're going to talk about first in, first out, which is modeled very well by standing at the supermarket. Okay, questions before I get going on the assignment or on the lecture? Okay, here's what we're going to do today. At least for the first part of the day, we might get to transition into something else, but depends on how much time we end up spending on this stuff. I've got some comments on homework 2, which we're still in the process of grading, and then we'll talk a little bit about lab 1, and then I'll give a quick Unix tip of the day. I'm kind of going to skip the Eclipse tip of the day, but I'll talk a little bit about it. And then we'll talk about sets, then we'll talk about these things called queues, and then I will talk about homework 3, which hopefully you got a chance to look at. If you didn't, please do it now. One of the big issues with homework 2 was people starting it way too late and then catching lots and lots of bugs and not having a chance to actually do it. Yeah? Is the timeline still being due for Wednesday? It's going to be due a week from Sunday now. So you've got an extra 4 days or something to do it. So I wanted to give you a little extra time because we're just learning about queues now. So yeah, that doesn't mean start it later. Don't postpone starting by more days. Just start now if you have it. Okay? All right, so let's see. The Unix tip of the day. So you might have done this before. You might have seen either of these before. So I've been doing Unix since well before all of you guys were born. And I literally just learned about Control-R completion a year ago. So there's things that you keep learning about in Unix. And I wish I'd known it before because it's actually really helpful. But there's these 2 things that when you're in the terminal, they help you complete what you're trying to type. Right? This tab completion is kind of neat. If you have let's say you have a directory here. And in the directory, there's all these files. This one happens to have hello output, hello world.cpp, et cetera. Right? And if you start typing something, let's say you wanted to print one of those out, CAT-H, and then if I type a tab right now, it fills in as much as it can of what is in your directory, and it says, oh, there's a bunch of things that start with HELLO, and nothing starts with HEB or something, right? The next thing that it can complete is HELLO, and then it stops and says, well, I can't complete any more than that, right? But if I typed capital O and then tab, it would say, oh, there's actually only one file called hello output.txt, and it fills the rest in for me. Pretty clever, right? The little tab works really well. So for instance, let's say you are on the homework and you want to copy the files for lab 2, right? You can go cp/comp/15/p for public, type tab, and it goes boop, and it fills it in for you, which is kind of neat, right? Public, and then let's see, labs. If I type L, it's not going to know because there's a couple things that start with L, like lectures and labs, right? But if I type tab twice, it will actually tell me what I've got in there. I've got labs, and I've got labs old. I don't know why I have labs old in there. But anyway, and then if I type LABS and then slash, and then let's say, let's see what's in there. Tab says, oh, there's index.html, there's lab 1 and lab 2. CDL, it will, let's see. Oh, sorry, lab/lab. It'll tell me lab 1 and lab 2. Let's say it's lab 2. F for files, maybe not. Lab 2 has maze solver, right. MA maze solver slash, and then so tab will keep telling you what's in the file. So it makes it really easy to fill in the rest of the details. Kind of a neat little one. Now, let's say that I typed something recently. Like I typed that CAT to start printing. Well, actually, I didn't. Let's say I type, let's see what I've got here. I don't know. Let's type out CD test. This isn't going to be good. This is not going to be good, actually. Oops, hang on. CAT time. Let's see. I'm trying to find a good file to type out. ls-als. Let's try alarm test.cpp. So CAT alarm test.cpp, and it prints it out for me. If I want to go and print that again, you guys know about using the up arrow key to get back, right? But there's a really neat one that if you don't remember exactly what command it was, or you want to go way back, Control-R says reverse iSearch, and then if you start typing like CAT, it will start going back to the previous things that you printed out. And if I type Control-R again, oh look, I actually printed something called point values out earlier. Control-R again, there's no more. Oh yeah, there are more. Cat aplume02.log, etc. So I printed some of these things out, right? So you can see what the previous commands by doing Control-R, and keep hitting Control-R after you've typed a couple characters, and it will go back in your history. So it's kind of a neat way to get more use out of your Linux terminal. OK, questions on any of that? Pretty simple stuff. OK, that was Unix tip of the day. Let's see, did I miss the Eclipse tip of the day? Yes, I'll do it there. I wanted to show you in Eclipse how to use the debugger to actually see links in a linked list. What you can do is you can have it so that you click on a link that you're in the middle of running your program. You click on a link, and then you can get the next and see what the next card is. And then you do next and see what the next card after that. And you can walk your way down the list. And it makes it really nice if you're trying to debug to figure out where did my program go wrong. You can see that, oh, the head is null. Or, oh, the node after head is null, and it should be another link. So it's, or another node. So you can use the debugger to do that. Right now, we're not going to take the time to actually look at that. But if you want help on debugging with the debugger, either the Eclipse debugger or GDB, come on to the office hours, and I can walk you through some examples. OK? Because it's not, there's a learning curve. But once you learn how to use the debugger, I think you'll be very happy with it. OK? Questions on that? All right. Comment on homework 2. So a lot of people on homework 2, we're in the middle of grading it still, and we've noticed something, that lots of people used these two functions, has card and cards in hand, when they didn't need to at all. And in fact, that's not a good thing in terms of making your program efficient. OK, let's think about this for a second. If we have a linked list, head, a couple links here, or a couple nodes, and then null. All right? What does has card do? If I type has card C do, and if it's looking through this, what does it actually have to do? Yeah? It has to go through all of them until it finds it or not finds it. What is the asymptotic complexity of that? N, or linear, right? So it's linear behavior to do that. Now, some people did the following. They would say something like remove. So for the remove C function, the first thing they would write is if has card C, or if not has card C, return. Or return a card, or whatever. That's one of the first things they would do. That goes through the whole list once. before you ever even do anything else. Is that efficient? Not efficient at all, right? Not efficient. So you don't want to bother doing that. If you want to remove the card, just walk through the list. If the card exists, you'll remove it, right? If it doesn't exist, you'll go through the end of the list anyway, and you'll do exactly what you would have done here. Don't go through the list twice when you only have to go through it once. Okay, so that's like not efficient. Same thing with some people used cards in hand, like for the function that was insert at tail. They said for I is less than or number of cards equals cards in hand. For I is less than number of cards, walk through the whole list, right? Why not just walk through the whole list and check for null at the last pointer? You don't need to call cards in hand at all. That means you go through the list twice to do that. So not efficient. Okay? Other things that people did. When you do a for loop, and it's not an intuitive use of the for loop, for instance, if you say something like for I equals 0, I is less than index minus 1, I plus plus, right? That index minus 1, is that, like, if you're reading this code, like when I was reading this code, I would get to index minus 1 and I'd go, why is it index minus 1? Why isn't it index? But nobody put a comment to that effect. Nobody said, I'm only going up to index minus 1 because I need to end at the previous to the one that I'm going to remove. Right? Why didn't you write a comment about that? You just assumed that, I guess, I'd figure that out, right? That's exactly the kind of place where you need to comment things. When you do something that's slightly odd, some people had index minus 2 for some reason, and that was, like, if you didn't comment that, I'm like, well, why'd you ever put index minus 2? And then we would have to dig in and read a little, and they go, oh, you're really stopping it like the previous, and you got some weirdness going on there, right? So make sure you comment things like this, okay? So I'm making the TAs look for this stuff. When you say something that's a bit off, like an off by one, or something that's not exactly up to a var, you better comment it to say why you're stopping a little early or whatever. Okay, does that make sense? Okay, things like that we need to start thinking about. So it's kind of like the next level of being a good programmer. Okay. All right. So let's see. So that was enough on comment on lab 1 or homework 2. Lab 1. So a bunch of students didn't provide lab 1. Who didn't provide lab 1? Raise your hand. Well, did you not provide it because you didn't know about it? Or you didn't do it? Because I don't have to answer that. But what I mean is some people in the other class said, I didn't even know there was a lab 1. So Piazza, I sent an email through Piazza, which should have gone to everybody, that said, do lab 1. And like 20 people or so didn't do it. If you were one of those people, I gave you a 0 on it, but email me and say, I didn't know about it, or tell me why you didn't provide it. Okay, and I'll open it up again if you've got like a legitimate reason, like, oh, I didn't know about it. Right? Try to provide those things. For those who did provide it, if you didn't get it working, you got 3 out of 4 points. What does that really mean? Like 1 point out of your lab is worth 0.1% of your entire grade for the semester. I mean, it's like a really small amount, right? So don't stress about like this. But what it means is you can't go in. For instance, last semester I had somebody in lab. I was running through the lab provides after lab, and I noticed that somebody had provided their lab like 5 minutes after going to the lab, right? And sometimes if you want to start the lab before and you do that, that's not what we'd like, but you probably could do that. This was not this case. The kid went in, he downloaded copied the files, did a make provide, and then left, right? That is not the point. So I gave him a 0, and he had no excuse. He's like, oh, I didn't know I was supposed to do the lab, or whatever. But anyway, so this semester we're at least letting you, like, we're taking a point off if you didn't actually get it working right, because I do want you guys to try to get it working right. Okay, that's all. It's not a huge amount of points, but try to get it working. Don't stress about it, but try to get it working. Questions on homework 2 or lab 1? Or lab 2, which was yesterday, the day before, but no classes. So yes?
What day are we supposed to have lab 2 provided?
I'd like you to have it provided by Sunday. I didn't turn lab 1 off until this morning, right? And but yeah, try to do it by Sunday. I'll probably grade it Monday or Tuesday or something. But I mean, grading is really an automatic script, so. Other questions? OK. All right. I already talked about the Eclipse tip of the day. So let's talk about these things called sets. All right. A set is a very easy abstract data type. meaning that it defines an interface and a bunch of functions, right? It's basically a list with no duplicates and no order. That's it. Okay, we could have talked about it from like day one, what a set is, right? It's a list with no duplicates and no order, much like a set in math class is, right? A set in math class, you could have a set that's like 4, 3, 9, not in any particular order, and there's no duplicates. Okay, generally in sets in math, you're not allowed duplicates, although it depends what you're using it for. But we're going to not allow duplicates in our sets. Okay, but we're not going to care about the order. You can build a set, because it's an abstract data type, you can build a set with a linked list or a dynamic array. I tend to think dynamic arrays are easier because they're faster in general than a linked list, but you could do either. For this week's homework assignment, we built a set for you. All right, you can go ahead and look at it. You can look at the operations. We didn't build a full set with all the different operations, but we did it enough to get for this homework assignment. And you can certainly take a look at it. Okay? Sets have a couple of functions. They have add element, which makes sense. You're adding something to a set. They have remove element, which means you're taking it out of the set and then returning it. That's what the element type means, right? Remove some element and return it to the calling function. It has a size, which tells you how many elements are in the set. And it allows you to check if a particular element is in the set, is element. Okay, it returns the true if the element's present in the set, which is nice because all these allow you to basically say, hey, I can put stuff in, I can take stuff out, I can find out how many there are, and I can check if it's present. Done. Okay, pretty easy to do altogether. Okay. We have some other functions that we could, if we wanted to implement. I didn't implement them for your set on the homework, but we could. Just like in math class, we could take the union of two sets. Right? If you have set 1 and set 2, the union is the objects that are present in one or the other altogether. Right? That's the union. Okay? We also could have the intersection, which basically, a little bit of math, says it's basically the ones that are overlapping in both. Okay, that's the intersection. You could also do subtraction, which means you take the ones from one set and subtract out all the ones that are in the other set and return the ones from the first set. Okay? So those are other functions we could look at. They're not mandatory for a set, but they're nice to have. Okay? If you make a set with a dynamic array, it's pretty easy, right? Add just searches for the element and then appends it if not present. Okay? Why do you have to search through a set before you add an element to it? No duplicates, right? Remove simply goes through, finds it. If it's there, it removes it, right? Size obviously gives the size. Is element searches for it and returns true and false otherwise. What's the asymptotic complexity of these operations? What's add? N, linear, right? Because it's got to go through and search all of them. In fact, the best case and worst case is linear. Because it's got to go through the whole thing to find it. Remove, what's the best case for remove? Actually, it depends. Depends how you're doing the searching, right? If you're clever about it and search from the end, then it's order 1, right, for the best case. Because you can start at the end. If it's that one, just remove it and change the size. If you're not clever about it and you start from the beginning, you got to move everybody back, right? So be clever about that. That could be that. But the worst case is what? And you have to go through the whole list. OK, what's the asymptotic complexity for size? Be careful. For a dynamic array, don't we have to keep the size around? So what is it? 0.1. It's constant. That's nice. And then is element to search, so. Can we do a binary search on a set? Not if we're not sorting it. If we did sort it, we could. And there are things such as sorted sets. But it's a little odd to have a sorted set only because you might as well do other stuff with it if you're going to keep it sorted. You lose some of the asymptotic complexity there. Okay, so everybody's order n except for size, which is order 1. Okay, pretty straightforward with these ones. Now. Union, intersection, and subtraction are interesting. For union, remember what union is. you've got two sets, and you're basically trying to say that if it's in one and it's in the other, put it in the new set, or return it in a new set. Does that make sense? To do that, you basically have to go through one set, and for every element in that first set, check every element in the other set to see if it's the same. That is what kind of asymptotic complexity? Quadratic or n squared, because it's a doubly nested loop. So union doubly nested loops with dynamic arrays are not fast. In fact, they're particularly slow because they're n squared behavior. Not good, right? If you have a set based on some other structure like a tree, which we haven't gotten to yet, you can actually make it log n for some of these operations. So it's not so bad if you're doing that. But if you're doing it with a dynamic array, then it would be n squared. Sorting the set would make it easier to do some of these things, because then your search can be a binary search, and you're going to get better behavior altogether. OK? So that's sets. Now, as I said, that's really all I care that you know about sets. Go ahead and look at the set we built for you if you want. You should know the operations you can have in a set. You should know some of the you should be able to work through the asymptotic complexity, but that's about all I care that you know. OK? One of those toolbox ones. Yeah?
What happens if you subtract like A from B and like the element in present in A is B?
Let's say you have a set that's just A. Let's say you have a set that's A, and then another set that's B and C. And you were trying to do A minus B and C. Well, what do you think gets returned? Empty set, right? So A minus BC actually it ends up being the empty set, which would be none in there, because that's what it's saying, right? Saying for everything in here, subtract out what's in here. And or in other words, yeah. So sorry, it means no. I did this backwards, didn't I? A minus BC. No, sorry, it would be this. No, this would actually give you A. I lied. Thank you. That will give you A. Because there's nothing to subtract out, is what it is. Sorry, I was backwards. If you said, let's see, how would we get the empty set? A minus AC or something, right? That would give you the empty set. OK, yeah, sorry. Why didn't you correct me? I think I'm doing some weird math up here. I'm not. OK, questions about sets? Anything else? Yes?
So it wouldn't give you A negatively? It would just
No, there's no concept of that. You basically say, if it's in this one and this one, don't put it in the result, right? But if it's in this one and not in this one, leave it. It's basically subtracting out anything that's in this one.
So we're talking about subtracting like items.
Yes, items, yes. Yeah, yeah. In kind of a math set theory type of way, which you might not know about yet, but that's all right. It's not the biggest deal. I won't make you do this anyway. Just know that you could have a subtraction type thing. OK? Anybody else? OK, if you're a Python programmer, you could check out sets, because they have a set class built in, and you could play around with this and see if it comes out with what you think it should. OK? All right. OK, enough about sets. So queues. OK? So I showed you at the beginning, I showed you the queue, or the line at the supermarket, right? And stacks or queues, just like stacks, are just lists of things. OK? It's another abstract data type. OK, we can build it using lots of different ways. But these ones are first in, first out. OK, queues are the first one in is the first one that gets out. It wouldn't be so good if you were standing in line at the supermarket and you got there first, and then the cashier came along and started at the back. Like, that would be a little weird, right? And then somebody else comes in, and then you just keep getting pushed back farther, right? A stack is a terrible way to do a supermarket queue, right? It'd be really bad. First in, first out is a model we use all the time. I got kind of upset about this first in, first out queuing situation when I was in 4th grade. There was I didn't know it was a queue, but I mean I knew about lines. I was standing in a line to go somewhere like lunch or something, and Gary Gerst comes walking along, and one of his friends was in front of me, and he did the old frontsy backsy thing. You ever know this one where you go to somebody and you say, look, let me in front of you, and then I'll let you in front of me. And then it's basically you're saying, let me in front of the guy behind you, which was me. And so I was not too happy about that. Turns out Gary Gersh is actually a great guy. And right now, believe it or not, he's the principal of that school. He's actually now the principal. And I hope he catches kids when they do this, but I'm sure he'd never remember that. But maybe he'll watch the YouTube and remember it. But he is, like I said, he's a great guy. So anyway, insertion is done at the end. You always talk about, and people kind of sometimes forget this. When you insert into a queue, you insert at the end, just like a line at the supermarket or a queue at the supermarket, right? You go at the end. Okay, that's where you insert. And you remove from the front. Okay, that's just how it works. We have some queue operations. One is in queue. Obviously means insert into the queue, but you insert at the end. Okay. We also have dequeue, which deletes and then gives you back, generally, gives you back from the beginning of the list, or the front of the queue, what we call it. Okay. We also have isEmpty. Now, isEmpty, this is kind of similar to you don't really need to call isEmpty inside your in queue or dequeue method, right? I guess if you're doing, especially if you're doing a dynamic array, you don't actually need to call that. Just use the fact that you know that it's got a size of 0. Okay? Don't go calling it. It's not your job in queue or dequeue to say to the user, I'm sorry that the queue is empty, right? You should, if somebody tries to dequeue from an empty list, you're totally allowed to crash. At least in our programs you are. Okay? If you try to dequeue from an empty list, you crash. So what happens? As the user, when you call dequeue, first, if you think that it could be empty, check if it's empty. See how that works? So do it that way. Don't worry about building isEmpty into dequeue. Okay? You're allowed to crash on that. OK, so those are some functions you can do. There are also some other functions. We've got obviously we've got the size, which tells you the number of elements in the queue. Okay? If you're doing a linked list implementation, that's going to be kind of slow. But if you're doing a dynamic array, you've already got it, so it's going to be constant. You can print the queue generally. You can take the print is a little weird. I mean, for our purposes, we're going to be able to print it. It's not normally a queue function, but you could. And then we've also got front, which peeks at the queue, which we call the front element, and back, which peeks at the back element. Okay? It doesn't actually return it to you, but it peeks there. Okay? What's interesting is this is different than a stack in that you actually get access to both the front and the back. You don't just get access to one of them. You do get access to both the front and the back. Okay? You can't actually remove from the back. Like there's no dequeue from back or something, but you can peek at it and see what you put there. Okay? All right. Questions on the functions? Okay. All right. Let's do a couple of examples here. Okay? Unfortunately, I should have done this. I should have put more values in here. Pretend there's more values in here. You don't have to, but pretend that the array starts there. Okay? What we do in a queue is we have these two values. Now, they are arrows, but they're not pointers in this case. If you're using a linked list, they could be pointers. I like to think, instead of pointers, think of them as indexes, right? Index, if we started here, this is going to be index 0, 1, 2, 3. Make sense? They're not pointers. They're just indexes into the array. What you do is you keep the front, an index to the front, and you keep an index to the next available spot in your queue. Okay? Why do we do that? It makes some other things a little easier later on. You'll see why later on. But do it that way. So this is not like a linked list where it's like the head and the tail. It's front, and back is the next available space. Okay? If you built this with a linked list, back probably would be the tail. Different situation. This is with an array. Okay? And you keep how big it is. Current size, actually, even with a linked list, you should probably keep a current size updated. Okay? You should keep that updated because later the math gets a little bit harder if you don't keep it updated. Not that the math gets harder. It's just you have to do more work and it's not as fun. Okay? Keep the current size around. Okay? Current size here, 4. Now, I'm going to go through a couple. Yeah, question?
For a size of 0, is the front and back point the same
Yeah, it's a good question. What do you guys think? Front and back, if the size is 0. Same, but there is no front, so you'd better check is empty, right? So if there were 0 elements, the front and the back would be at the same place, and that would be the next available spot. But if you tried to check it, if you tried to DQ, then things would get screwed up. So you got a bit of an issue there, right? Yeah, good. Yeah.
It's a bit of an issue of memory management aspect because you hit the tail of the memory array to keep chopping the whole front.
Yeah, you're stealing my thunder, which is fine, but that's a very good question. Keep that in mind in about 2 slides. Well, maybe 3 or 4 slides, but maybe 2. We'll see. But it's going to be, you'll see. So the question was, hey, isn't there a memory management issue here? Especially the way I drew it with all those empty bits up at the front. Yeah. So some things are going to have to be, like, we're going to have to figure out a little bit about this, right? Before we get into that, here's how you enqueue into a queue. OK? Well, you know where the next empty spot is. OK? So you put the element there, right? Then you increment back, because now back is not there. Back is going to be here, the next available spot. And you update the current size to be 5 in this case. OK? So if we're enqueuing 8, first thing we do is put the 8 where back is. Then we increment back and increment current size. So now we've just enqueued 8. Make sense? Not too hard to do. Okay. To DQ, right? To DQ, you simply return what's at the front, because that actually has the index of the front. Return that value and increment the front. Pretty simple, right? They're pretty simple operations. Okay. Return 5 and increment it to 2. Now, what do we do with the 5? Should be deleted. You can leave it. Any other ideas? There are other options here. Good options. Deleting it, probably not. And from a dynamic array, unless we redo the whole array, we're not going to want to delete it. We can, do you say leave it? That's not a bad idea either. There's one other option that wouldn't have entailed doing it exactly like this. What do you think? Make it null. No, it's going to be some value, let's say. So we're not going to make it null. We're not going to really delete it. We could have done this. We could have been sneaky about this. And we could have said, or we could have been actually not so smart about it in this case. Forget about what I said about enqueue or dequeuing. You could have returned 5 and then moved the whole rest of the list back here. What's the asymptotic complexity of that? Linear, right? What's the asymptotic complexity the way I've done it? Constant for both enqueue and dequeue, right? So we don't want to do it. We don't want to leave the front there, although you could. OK, you could leave the front there and then move it back and forth, but that would be silly because it would be asymptotically not so good. The way we've got it, we actually have constant behavior, which is what we love. But first of all, we don't need to do anything with 5, as it turns out. It's just a dead squirrel. OK? What is the problem with this, though? And you were hinting at it a little bit earlier. Want to keep going on what you think's the issue here?
Well, every time you DQ, you leave empty array elements in the front.
Yeah. All this stuff is dead squirrels. And then what?
Can't use it because of the front.
Can't use it. And then what happens later? Let's say I enqueued 10 and then I enqueued 15.
And the issue is that your dynamic array is going to tell you to.
Yeah, your dynamic array is going to be in trouble at that point, right? Not in trouble, but you've got to expand, right? And now, if you were clever about it, you could do this, and then every time you got to the end, expand, right? And to expand this, we would just double the size, copy everything, including all those dead squirrels, and keep on going, keep on going. Ooh, that hurts, right? That hurts because anytime you're going to copy dead squirrels is bad news, right? You don't want to do that if you can help it, right? You don't want to copy stuff that you're never going to use again. Why bother? Maybe we could be kind of clever. Maybe this is what you were going to say. We could be kind of clever and say, oh, I know where the front is. Just copy the front to the back. Is that what you're going to say? So just make a new array. In fact, make an array that's maybe the same size. Who cares about doubling it? Make it the same size and copy just these guys. Not a terrible idea, but you're going to be doing a lot of, if you enqueue, dequeue, enqueue, dequeue, enqueue, dequeue, enqueue, dequeue, right? You're going to be doing that, doubling the size of this pretty often, right? Or changing it. One sec, Nathan, then go, sir. Yeah, Nathan.
Yeah, why can't you just, or I guess this is, why can't you just like slide all that
Yeah, you could slide it back there. That's a good point. It's order n. That's one solution to it. I will wager with you that we have a better solution. It's a good point. One sec. Sarah?
You've got access to all of those, so then you're keeping track of front and back. Why don't you loop around and
Is that what you're going to say? Is that what you're going to say? Why don't we just loop around? In other words, do a little bit of math and keep track of where in this whole thing we are. No? You're laughing because it's crazy or crazy talk?
I'm going to mess up that for loop.
You're going to mess up the for loop. We're going to practice one of those for loops in a second. But yeah, so that's wasted. We've all got that. That's wasted. There's the front. The back is now out here, so we have to expand. But why waste the space? As Sarah said, we can actually reuse that space if we're a little clever about it. Yeah, if you're.
But once you're out of those spaces and you try to expand.
Once you're out of those spaces and you try to expand, it is a little trickier. But guess what? We're going to do that, and it's not the end of the world. I promise you, it's not the end of the world. OK? All right. So watch what we can do. OK? First of all, most queues, if they're working properly, will enqueue and dequeue at about the same rate, right? Unless you're Comcast and you're like a hold line at Comcast, right? Which basically I think theirs is just like, I don't even know what their model is. It's basically a list that just they never dequeue. They never take anybody off the list, right? I'm sorry, your hold time will be 4.5 hours, whatever, right? But if you're running a supermarket, for instance, you want people in the queues because you want to sell stuff. But you don't want the queues to be down the hallway and back to the produce section, right? You want them to be enqueuing and dequeuing at roughly the same rate throughout the day, right? So you never have more than 5 or 6 people in the queue. And that's probably even too much for a big supermarket, right? If you have a few people in the queue, that's probably good. If it's at the same rate, you will be able to do this. You will be able to use this many items in your queue for a long time, maybe. Unless there's a run on milk or something, and unless there's a snowstorm, right? In which case you need to make your queue bigger, right? But for the most part, you're going to be able to do this. The first time I ever saw this, well, I'll pause on that. I'll tell you about that in 1 second. I want to get to what we actually do here. What we can do is we can implement this circular queue. Okay? It's called a circular queue because it circles back around. Okay? Instead of making back go out here and having to expand, these are all dead squirrels. Everything from front back this way is a dead squirrel. Put back here, who cares if it's a dead squirrel? Put the back at index 0, and now you are ready to go. And you can enqueue here, 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 and here before you get into trouble. Right? So that's how we do it. Now, the question is, how do we make sure that back doesn't go here, but goes down there? OK. Let me do it on this one. How are we going to do that? Yeah?
Could you make it like this back is greater than the front side?
If back is greater than, let's use capacity, right? Because the capacity is kind of what we normally call it in here, right? If back is greater, so first we're going to do this. We're going to increment back. So let's first do that. Back plus plus. That's what happens there. Then you say, if back is greater than capacity, right, you're going to say back gets what? That is a perfectly legitimate way to do this. However, this takes 2 statements, an if statement and a statement like this. There is a way to do it a little bit better. Yeah? You can use a modulus. Now, remind us what modulus does.
Takes the numerator of x divided by y, divides that, and takes the remainder.
Remind us like we're 5. Gives us the remainder. Perfect. OK. So you divide 2 numbers, and the remainder is the modulus operator. OK, let's practice this. OK. What is 10 modulus 10? 0. What is, let's use another example. Let's say 10 modulus 4. Oh. 10 divided by 4 is 10 divided by 4 is, why do people keep saying 8? 10 divided by 4 is 2 with how much remainder? 2. This is 2. That was a bad example. How about 10 modulus 5? 0. OK. 10 modulus 1. 1. OK. 10 modulus 3. OK. 10 divided by 3. 3 goes into 10 3 times with 1 remainder, right? OK. Good. 3 modulus 10. Yeah. 3 divided by 10 is what? 0 with how much left over? 3 left over, right? So these are the ones that we really are going to care about in this case, right? This one and like this one in this case. So what you can do is you could say, right, after you instead of doing back plus plus, do you have what you go ahead?
Yeah. So I'm saying you increment back, then you do modulus using the capacity, and then after that you have to check and make sure that you're not at the same spot as front. That's what we make it.
Hold on. Back plus 1 what? Modulus capacity. So first of all, that will actually give it to you, right? Because what you're doing is you're saying back gets back plus 1 modulus the capacity. And if the capacity in this, if it was 10 and you were at 9, right? 9, remember, is the end of the 10 element array. OK? 9 plus 1 gives you 10. 10 modulus 10 gives you 0. That puts you back at the beginning. OK? So this would actually work just fine. Back equals back plus 1 modulus capacity. Now, normally what we do is the first thing we do in, say, an in-queue is check if it's full, first of all. So we wouldn't necessarily need to check that now. This would be if you're in-queuing, like at the end of in-queue. OK? Question?
How do you tell the difference between one that's full and one that's
That's a very good question. If back is the same as front, you could either have an empty queue or you could have a full queue. And what you have to do is you have to be a little clever about when you do the check. And you also have to be, you could also, if you keep the size, the current size updated, you'll know that current size is equal to capacity. That's normally what I would do. I would say if current size equals capacity, expand. OK? Yeah?
If you're searching through a queue that's wound up going circular, so the back points to the very front,
Yeah.
somewhere
Yeah.
in there, and the front is after that, how do you get through the end of the array?
OK, first things first. You can't search through a queue. Not allowed. OK? That's one of the downsides, I suppose, of the abstract data type. Right? How do you search for something in a queue? If I wanted to know if, let's see, a bad example for this one, but if I want to know 3 was in the queue, I would dequeue this one, and maybe store it in another queue, and then check this one. Dequeue this one. If I wanted to get it all back, dequeue this one, send it to some other queue, and then re-enqueue them into this one. There's no way to search through a queue like that. OK? Yeah?
If it's just an array, why can't you search?
Well, you could, but then it's an array. Right? According to the queue abstract data type, you're not allowed to do anything but enqueue, dequeue. Right? And it's so that you're limited. I mean, you are definitely limited. And in fact, one of the things for this homework assignment involves doing exactly this. Telling if a student is on a wait list, you're trying to search through the queue, I'm not going to let you. Right? I'm not going to let you search through the queue. You have to go through the motions of dequeue, check, re-enqueue everything. OK, I want you to go through those motions. Is it pedantic? Yes, but I want you to do it. OK, but yeah, so yeah, you're absolutely right. I mean, if you're building this and you said queue plus ability to search, sure. But in a queue, no, you can't do it. OK? All right, anything else? Let's look at this circular queue in better detail as far as an example. Here's what I'm going to do. I'm going to put the original up here, the next step down here, and then shift these upwards. OK, so this one will be the one we just did, and then this is the one we're going to do. So in this case, if we start with a queue that looks like this, the front is here, the back is here, and our current size is just 2, because there's 2 things in the queue. All these other ones could have values in them. They're just dead squirrels at this point. OK? All right. If we want to enqueue 1, what we do is we put we put the 1 here. OK? Put the 1 here, and then increment back using our fancy back equals back plus 1 mod capacity. Or we do this. And I don't care which one you do. I'm not going to take off points for doing this extra step. That's not inefficient enough to care about, right? In fact, this might be a little easier to read in terms of like comprehension, right? But this is probably the way I would normally do it, just because it's not too hard to read and kind of normally the way you do these. And then back ends up at 0, and front ends up here, and we increment the current size to be 3. Good? Now you've got the situation like this. Let's say that we enqueue something else. Let's say that we enqueue 3. So here's what we just had. Now we're going to enqueue 3. We're going to put it at where back is, increment back using this fancy one, and then increment the current size. There are 4 things in this queue. So far, so good? Yeah?
This might be jumping, but what happens if we dequeue and back is at index 0?
If we, where do we dequeue from?
Right.
The front, right? So we're always incrementing. We're never decrementing these front and back. They never get decremented. They always get incremented. Right? Yeah, good. OK, so after enqueue, that's what it looks like. Let's dequeue a couple things. OK, let's do 2 dequeues on this. Dequeue this. The 8 gets returned. We increment front. It ends up here. We dequeue this one. We return 4. We increment front. It ends up here. And this is the final situation so far. Now we're going to dequeue again. Right? Well, to dequeue, remove the 1. Here, I'll do it on the next one. You remove the 1. Right? And then increment front using our fancy go circle around statement. Okay, you increment the front, and it ends up over there. And how many things are left in the queue now? Just 1. These are all dead squirrels. But notice, we haven't had to expand anything. And by the way, we've still got 10 elements, and we've only got 1 thing in the queue. So we haven't had to expand, and we won't have to expand until a net of 9 more in queues. So if we dequeue, enqueue, dequeue, enqueue, dequeue, enqueue, dequeue, enqueue, you could do that all day and still only have a queue size capacity of 10, which is kind of one of the neat things about this. Yeah?
So queue is really good at adding and removing elements and really bad at holding a lot of stuff in the queue at once. Or it's not designed to hold a lot of stuff in the queue at once.
Yeah, the queues generally aren't designed to hold a lot of stuff, but they can expand. And we will expand this one in a second, these in a second. But yeah, that's a good point. That's a very good point. Okay? So I was going to say where I first saw a circular queue before. So back when I was like a kid and started programming, which was like forever ago, the original IBM PC, which I actually had one. I didn't have it right when it came out, but I had an original IBM PC. And I was doing some programming on it, learning about these things. And it turns out that the keyboard, and this is still true for your computer today, the keyboard, when you hit a key, well, the computer might be doing something. Once you hit a key, the computer actually stops doing everything, gets that key, and then it doesn't necessarily want to deal with it yet. It basically says, fine, I'll grab your key, but leave me alone until I get some other stuff done. Right? So it takes the keystroke, and then it puts it into a circular queue. Right? And then it might be still doing some other stuff. And then eventually, within a millisecond or two, it comes back to your circular queue and gets that keystroke. But if you're like a super fast typist, you can type faster than the computer might be able to get back to it. So this queue just keeps like a circular queue of keystrokes. I believe when I was looking at it, it was about 128 keystrokes, which seems like not that many. And in fact, sometimes if you get that buffer full, you'll hit a key and it'll go beep. And that means, oh, it's not actually going to take that because the buffer is, the circular queue is full. It doesn't expand it. Right? It doesn't bother expanding it. It says you get 128 keystrokes. If I'm still busy when you've typed 128, you're going to wait. Right? That's what it says. But that's exactly what it was. And it's kind of neat in the sense that you get lots and lots of use out of it without expanding it. Right? It was very rare that I got that beeping, unless I wrote some program that like was in an infinite loop. Right? And it never looked at the keyboard. Then it would do that. So these circular queues are used for a fair amount of things in programming. Okay? All right, so let's see. So that's after we dequeue. Let's dequeue one more time. Right? And now if we dequeue one more time, we return the 3, move the back to the front, and now we're back to an empty queue. Okay? And again, one way to know if it's a full queue or an empty queue is to see what your current size is. And if it's 0, it's empty. Okay? All right. So that's how we do that. Okay? You can, if you don't keep current size, you could do this. Back minus front plus the capacity, mod the capacity. That would give you the current size, but it wouldn't work for expanding, would it? I think that would probably be the problem, because if back and front were the same, let's say they were both 3, you'd still get a current size of 0. So you can use tricks like this, but you just have to be a little careful to know, to somehow keep track of whether you're full or you're empty. It's a little bit trickier. OK? All right. Now, when you do reach capacity, okay, when you do reach the capacity, then you do have to expand if you try to enqueue again. Okay? Or you have to beep at the person. But let's say that you're going to expand. Right? Think about how we would go about expanding this. Okay? Actually, do this. Talk to your neighbor for a minute. Think about how I'm going to draw this on the board. Think about how you're going to go expanding this. Okay? Do that. Talk to your neighbor. Say, how would we go about expanding this like we might a regular old dynamic array? OK. Anybody think about it? Are there some interesting issues about expanding this? Yeah, there's some interesting issues about expanding this. Now, I rewrote this, except I just changed them to letters, because when you're talking about indexes and like actual elements, it gets a little weird. So I wrote it like this. So forget about that for a minute. If we're expanding this, and let's say that this is both the front and the back. So the front and back index is 7. OK? All right. First things first. And I know you guys thought about this, but first things first. What do we have to do if we want to make this expand this? Make a new array. How big? Double. OK. So let's do this. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That should do it. OK, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, dot, 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 dot. That's all we need. OK. All right. You could, just like a dynamic array, copy these straight over. Is there a problem with that?
The first,
Winona?
the ones that are supposed to be in front, X, G, and R,
Yeah?
those are supposed to be first elements of the array, and then when you copy the last 3 elements.
Yeah, if you were to copy this directly, aren't you in the exact same problem? Don't you have the exact same problem you had before with basically if 7 was X and the front and the back were both here, how are you going to, like, you could increment the back, but then if you were to add one, but then now you've got a problem where you like dequeue, and that's the next one. So it's not a queue anymore, really. Right? You've all of a sudden made them go out of order. You can't just copy them straight down. OK? That would be like, that breaks your whole queue thing. Winona, did you think about how to do it?
Yeah.
Go.
Could you decrement back and then go from front to back?
Could you decrement back?
Yeah. Like move back to 6,
Back to 6.
and then go 7, 8, 9, 0, 1, 2, 3, 4, 5, 6.
7, 8, 9, and 0. Well, kind of. That's, yeah, I wouldn't bother doing the decrement of back yet. But I like where you're going with this. OK? Who else thinks they know? Yeah, go ahead.
So if you have a counter that starts with 0, so the first array f would go from 7, 8, 9, so you keep incrementing front
Yeah.
until front is again equal to back.
Okay. Ooh.
And then once you've done that, you know all the new elements have been copied in.
Okay.
So just make front equal to 0 and back equal to capacity, and then you have.
So okay. So what is this one going to look like at the end of yours?
It's going to look, instead of being ALMC, it'll be XGR.
Ah. Okay. So I like what you're doing. I think your explanation of saying front equals back, I don't know if that's necessary. But does it make sense to everybody that really if we did this, this is the front, and it goes X, G, R, A, L, M, blah, blah, blah. If we just started this one at X and got everybody else after that, we'd be in perfect shape, right? Because that's the actual, that is the actual back to front in that case, or rather front to back in that case, right? So let's write a for loop to do that. For I equals 0, I is less than what? Initial, let's say, yeah, we'll call it the capacity still. Let's say this, we haven't updated capacity. Let's say capacity. What's going to happen to I? I plus plus. OK. And then now, we're going to copy things into, let's call this one our Q. It's the only, like this is the only data structure or abstract data type where you can name the object with one letter and it's correct. It sounds correct, right? That's Q, which is a Q. Right. We'll call that Q. We'll call that Q. We'll call this Q2, as in the new one. OK? All right. So where are we going to copy from and where are we going to copy to?
Why not just do
EQ, NQ?
Yeah, DQ from the first Q and then NQ.
Oh, you could do that. You could DQ from the first Q and NQ into the second Q. In fact, that's one of the things you'll probably want to do for your homework assignment, that for when you're copying an entire array. OK? You could do that. Let's just write a for loop so we don't have to go through the whole business of updating front and back and blah, blah, blah for both of them. That's just not so efficient. I think we can do it with a for loop. That's a good idea. Let me start you out. Q2 something gets Q1, or I guess it's just Q. I'll do it down here so we have enough room. Q something. Maybe that'll give you a hint that that's going to be a little bit better. OK? Talk to your neighbor about this. Should figure it out. Sorry, is it hard to see from over there? Is it hard to see from over there? OK. OK. OK, who thinks they've got it? Danielle. Sorry, go ahead. Q2 of I gets Q of front plus I modulus capacity. Now, let's see if that works. I like it. Let's see if it works. OK? Q2 of I, that means we're going to start at 0 over on Q2. I like that so far. Front plus I, well, I starts at 0. So front modulus capacity, what did we say 4 modulus 10 is? 4. So front modulus capacity, when front is not at capacity, is going to be equal to front. So we're going to start out and get 0 gets 7, because front is 7, right? Which was x. I like it. I is now 1. Q2 of 1 gets Q2 a Q of front plus 1, which is 8, modulus 10 in this case, which is 8. G. Okay, let's assume that the next one works, because it's the exact same idea there. And then let's do the next one. So for Q2, or for I equals 3, right, we're going to say that Q2 of 3 gets Q of the front, which is 7, plus, Q of the, plus I. 7 plus I, which is 10. 7 plus 3 is 10. Modulus 10. 10 modulus 10 is 0, which means it gets A. Same thing for L, M, C, B, Z, and N. Where do we put front now? Front is here. Where do we put back? Capacity, 1 after where it is. And now you've properly copied your Q, or expanded your Q. Make sense? There are other ways to do it. You could have it somehow where you copy them kind of directly, but somewhere it's well, not directly, but you could copy like this part to here and this part to the end and have the middle part, but don't bother doing that. Right? This way just makes it nice and straightforward. Okay? Yes, question?
Is there any reason why you can't from the first one?
Yeah, you could. You could. That Nathan asked that earlier. You could. But the thing about that is, if you DQ from this one and NQ in this one, you've got to keep back and front moving along and back and front moving along, and it's just more work, right? A for loop will work just fine. But in this case, you'd have to, and by the way, this is just an array, so you would, in your case, you'd have to like create a whole nother queue, and well, because you can't DQ from an array, right? It's not like you're passing in an array to DQ. You're DQing from this array and in-queuing into this one, which is not this. If you were to DQ, right, before we even have this one, DQ puts it in this array. Where does NQ do? Or DQ takes it from this one. Where does NQ put it? In this one. So there's more work to be done if you wanted to do that. Technically, you could. You could move this back. You could just do that process. But why do it when we can do a for loop that makes it a little easier? OK? All right. Any questions on that? You'll do this for your lab on, I basically did your lab for you on Monday. But you'll get practice of it anyway. OK? All right. So where do we find queues in real life? Well, lots of places, right? If you submit your job to a printer, like the printer or whatever, right? You hope that yours gets spit out first if you put it in first, right? Printer jobs are a little weird in that you can actually delete from the middle of a queue, so they're not quite queues in that sense, but they're modeled otherwise like that. Ticket counters, supermarkets, right? It would be really bad if you modeled your supermarket on a stack, like I said, right? You don't want somebody who gets in the line first to never get out of the queue, right? File servers, if two people on the file server ask for the same, when you're all furiously typing that CP command in lab, right? You're all asking for the same files, right? And when the person that hits the enter key first generally gets the file first. Okay, it's just a queue. Call centers, we talked about that. Next available agent, right? My research was on CPUs and GPUs, your central processing unit and your graphical processing unit. And in these days, you can actually do regular old computations on both. My research was all about taking work that you have to do and feeding them to one of either the CPU or the GPU. And it's a perfect model for a queue. In fact, this is an actual slide from my dissertation defense, which says applications are moved from a main queue into a device subqueue based on a set of rules, and here's all the rules. Right? So I had to learn all about queues and the best way to use them and so forth. So it was straight from my research. Right? So you use queues in a lot of different applications. All right? Questions on queues in general? OK. Let's talk about homework 3. So homework 3, first of all, I moved the due date to Sunday, a week from Sunday. All right, I'll probably actually put out homework 4 before that date, just because why not? But the actual date for this one's Sunday, the 22nd at midnight. Please don't just say, oh, good, I've got 3 more days to start it, because you really don't. Okay? It models a class roster. Now, this is where, like, so you sign up for a class or a course, right? And especially in the computer science department now, where classes are just too big and not enough people to teach them and whatever, what happens is if you're a major, you end up going into the class until the class gets full, right? And then you end up going onto a wait list, which is just a wait list for majors or engineers or some other one-off types of things. If you're not a major, they generally don't let you enroll in the class at all. They immediately put you on a wait list. Okay? And then after they increase the capacity, then people start coming off these wait lists. But who gets priority off the wait list? The majors, right? So all the people from the majors come off the wait list. And then if there's any room left, the non-majors can go on to the regular roster. So this is the model of that. Okay? And this is what the program actually does. Okay? There's a file. I'll show this to you in a second. isiscourse.h. I called it ISIS because, you know, we love ISIS so much. It's called isiscourse.h. And that has lots of information about how this is implemented. So if you're asking yourself, wait a minute, what happens if to a major, the major waitlist is full? Well, there is no waitlist like major waitlist being full. It can be infinite. Right? Or what happens when somebody's added to the course or drops the course? Well, we've got details about that in there, so you should read that. The basic idea is this. Students attempt to enroll. The course isn't full. Majors get in until the waitlist is over, until the course is full. And then others go on the other waitlist, and the majors go on the major waitlist. And then you have to figure out the details of that. Okay? Let me show you a couple things here. Let's see if I have this up. isiscourse.h. So in isiscourse.h, I know it's hard to read the font. I can probably do this. A little bit bigger anyway. OK? This is all the details I was talking about, right? It gives lots of details there. It gives more details about down here. Somebody in the other class said, what is this enum thing? Anybody see that in a couple of programs and go, what is that all about? It's pretty simple, right? All enum is used for is for humans. Right? It's so that humans don't have to remember that we said that in none is 0, enrolled is 1, major waitlist is 2, and other waitlist is 3. When you say enum and give this is a type. You've all of a sudden defined a type called enrollment status. And the only things that enrollment status can be are none, enrolled, major waitlist, or other waitlist. Under the covers, none is 0, enrolled is 1, major waitlist is 2, and other waitlist is 3. And that's it. Right? So you have nothing else to it, except that it's now a type that you, as a programmer, can go around and say, oh, somebody is enrolled, or somebody is on the major wait list, et cetera. OK? So you can do that. And in here, you can actually return an enum as a type. Right? So if you say, let's see, well, enrollment status. If you attempt to enroll a student, right? If they go on to the wait list, or if they go into the class, they end up as enrolled. And you return enrolled. What are you really returning? You're really returning, what did I say? 2 or 1. You're really returning 1. But that's hard to remember. So as humans, it's easier to remember, oh yeah, the student's enrolled. Right? So that's all the enum is for. OK? Questions on that? Yes? No, you return enrolled. Yeah, that's all. If you return 2, it might whine at you about, like it would probably give you a warning and say, that's not an enum, even though really it is. You could cast it to a 2 and it'd be fine. But don't return 2, return enrolled. Right? Actually, it'd be 1, even. Right? You don't even need to remember it. Just remember if they're enrolled, you return enrolled. OK? All right. So that's ISIS course. You also have to write the queue functions. Right? And I've given you a blank queue.cpp file. So you have to do the whole thing. Right? But you have to create, obviously, you've got a couple things in here. This is my version, by the way. You don't need to worry about these things, although this brings up a very good point. If you have a queue that looks like this, and it's called queue, and you had a new queue, let's say you had a new queue, Q2. You cannot say Q2 gets Q. Sometimes you can say that. With cards, it turns out it was OK to say that. With queues, because there's more pointers and stuff going on, You are not allowed to say Q2 gets Q. Unfortunately, the compiler will not whine at you and not give you a warning, and will let you do this until you rip your hair out, right? And then even more. It'll go, yeah, you want to do that? Go ahead. You know what you're doing, right? Turns out you don't know what you're doing. But what happens is when you do this, it basically, under the covers, it basically says, OK, now Q2 and Q1 point to the same array, which is probably not what you wanted, right? It's a little more subtle than that. What you can do, and I'll talk about this next week, but what you can do is you can create this thing called an assignment overload. And it's got some funky syntax in it, right? It returns this operator reference, which is a little odd. It takes a reference, which again is odd. You probably didn't do anything with references in Comp 11, did you? Not pointers, references. A little bit, yeah. They're a little bit, but anyway, what this does, this operator equals overload basically says, to the compiler, if you see Q2 gets Q, don't just do what you think you want to do. Call this special function, and I'll tell you how to do it. And it will do a proper copy of the actual Q. So then Q2 is a whole new object, OK? If you want to do this in your program, you have to write this overload function, which is basically the same as saying DQ from this one in Q into this one, right? It's pretty much the same idea. So I would stick to doing that. If you want to do this, we'll talk about it next week, but you do not have to. OK? All right, other things you have to do, you have to implement the InQ, DQ is empty. Right? And then you've got, because you've got some, because I suggested doing this with a dynamic array, I put the dynamic array stuff in here. You need the capacity, you need the size. If you want to do it with a linked list, you're welcome to. I would argue that this is an easier way to do it with a dynamic array, but you're welcome to do it with a linked list. It's up to you. But you're going to have to implement it. You can take these out if you're going to do a linked list, some of them. Questions? OK. So unfortunately, we didn't get to the other stuff today. We'll be a little behind for another couple days. But remember, no class on Monday, unless they change things. And then class on Wednesday and Thursday. See you guys later.